Morning. All right, we wait for some time for the people to come in. Do you have any questions on the lectures which were? Everything is good, understood. Okay. All right, then, well, if you can still try to ask some questions, because I still, well, we wait for some more people, so always sit in silence. So whatever you prefer. I'll erase from the board. Okay, so the reminder of the last material, we learned an approach to the statistics of Jacobi metrics, which is significantly simpler, where you can actually study the coupled evolution of two unit vectors. Each one of them defines a stationary process by multiplication with matrix of velocity gradients, and study of joint distribution of integrals of resulting stationary processes provides the statistics of the largest and smallest axis of the ellipsoid. So you can then, because of incompressibility, this provides the complete statistics of dimensions of the ellipsoid and gives you a shortcut to the statistics of the Jacobi metrics. So then we studied major stretching direction. We understood it as a direction which where locally things which were stretched for some time in turbulence are pointing. Now, you do not need any kind of special, well, long-term calculations for that, because this, the relaxation to the same direction happens quite fast. It usually takes several Kolmogorov times. So it's not something which kind of demands long time for determining, and usually it is determined actually by going backward in time, considering evolution backwards in time. All right, so we wait still a little bit, and then we start the lecture. All right, so today we will speak about let's see. Okay, so we are 10, it's too little, so 9 participants. Okay, maybe you can present some of the difficulties which you had, because also the course organizer is still not here, so it's not really good to start. If not, we will not wait anymore and start. All right, so today we will start from getting a connection between the generalized Lyapunov exponent and the statistics of singular eigenvalues of Jacobi metrics. And here I want us to train this language, which is that singular eigenvalues. It's kind of a name which you didn't hear before the lectures, I think, and it tells you eigenvalues of W transpose W rather than W itself. So then we define for the moment two different functions. So let me, and after we talk of this, I'll give you another application, which is of generalized datum of exponents, which is 2 dimensions of fractal attractors. So we'll speak a bit about that. What is attractor? What is fractal attractor? And how you calculate its dimensions using generalized datum of exponent. So for the moment, well, this is not really a good color. Let's see if we can get it better. Between good. Okay, let's see if this works. Between, okay. Gamma of k and s of rho 1, rho 2. Okay, so s is the large deviations function, and I would need to get more colors for the last lecture. All right, so we have 2 different objects. So I'll still try to do it. So gamma of k is an object which tells us what is the limit of time as time goes to infinity of well, the board is blurred. Okay, please let me know if something like that happens. So we defined it as logarithm of distance between the of moments. So it's logarithmic growth rate, and it's something which, if you think, you would think that this is well, since W has this structure that it's R times exponential of rho 1, 0, 0, exponential of rho 2, 0, 0, exponential of rho 3, and rho 1 grows more than anything else, then at large times you can think that R of kt would be like exponent of R1. So you could think that this is limit as time goes to infinity of 1 over t logarithm of average of exponent k rho 1. And the reason is very simple, that the same reason we used in considering major stretching direction. So we saw that W acting on any initial vector, it is R times lambda n R, where R and n are orthogonal matrices. I remind to you, I will make an effort to refresh everything in your memories. So n is the matrix which at large times becomes constant. It is the matrix which provides you with initial directions which will stretch at rates lambda 1, lambda 2, and lambda 3. R is the matrix which provides you with spatial orientation of this ellipsoid into which infinitesimal ball of particles evolves, and lambda provides you the length of the axis of that ellipsoid. So these are kind of all quantities here have immediate physical meaning, and therefore, because at large times,
Itzhak,
yes,
all these approximations, well, not approximations, analysis are for Jacobian being constant. So this is not time changing W, this is a constant W. And I'm checking if I understood correctly, this hyperbolic approximation of the flow is when you assume the statistics for W constant, no?
What do you mean statistics constant?
I'm saying that...
Please rephrase if you can. Okay, are you telling that you understand that W is a constant matrix?
Yeah, that's one. Yes, that's one of my questions. Is, are you taking W constant right now? for all this analysis?
Okay. Well, the short answer is, of course, no. However, it's the question which you ask is a bit worrisome because, well, it means that things were not completely understood. So let me make an effort and tell you. So I can see where the confusion comes from. It's apparently because I told you that effectively every point is a hyperbolic point. So you need to understand in what sense it is and in what sense it's not. So W is never a constant matrix, even for constant flow, which is hyperbolic point. In that case, it's exponential. So it's in any case, it's never constant. So let me remind you what is W. So Wik of t and x is derivative of Lagrangian transformation of space with respect to the initial coordinate. So this matrix depends on time, as you can see from the definition, and we learned many times in this way. So for matrix W to be constant, you must have 0 sigma, and this is not something which happens in turbulent flow. So W is a matrix which changes in time. Now, there is a simple flow which is called, well, kind of hyperbolic flow, where you actually have matrix sigma. So this is kind of a simple example. It's not what we are considering, it's a simple example where this matrix of sigma is diagonal, and it's given due to the fact that incompressibility implies that trace of sigma is 0. It is this. Now, in this case, W is very simple matrix. You can readily see that W is exponential lambda 1t, 0, 0, exponential of lambda 2t, 0, 0, 0, exponential of minus lambda 1 plus lambda 2 times t. Okay. So this is for this very simple flow. So the only thing which this flow does is that if you plot it, so you have the axis of coordinates, then you have, say, let's assume that lambda 1 here and lambda 2 are positive for the sake of this example. So then what happens is that you have that trajectories designated by streamlines along these lines go like this, and here they go like this. So what it means is that any ball will be transformed into this pancake structure. Now, in some sense, something very similar happens in the turbulent flow. So there must be no problem whatsoever for you to understand this example. And if we compare it with turbulence, we see that there is similarity. So in the limit of large times, in fact, if you take time which is large enough, then you will find that the W is actually, so for turbulence, okay, okay, let me keep this example and compare it with turbulence. So compare with turbulence. Now, in some sense, it's very similar. So you can, as time goes to infinity, in fact, you have that W is R times exponent lambda 1t, 0, 0, up to some small corrections, exponent lambda 2t, 0, 0, exponent minus lambda 1 plus lambda 2 times t n. Now, this is not an approximation. We're not doing any kind of neglecting something or something of that sort. We are actually doing some very general calculations, which are exact. They don't assume anything about the velocity field. It can be whatever it is. So the only difference between these cases is that you also have two rotations. So you understand that the difference is, in some sense, is not that, well, not in some sense, it's not that large. You have, okay, this ellipsoid also rotates in space, but, well, it's not, as long as you only care about dimensions of geometrical figures, you don't really care about that thing. So in this sense, every point in the turbulent flow up to these points which have zero total volume is a hyperbolic point. In this sense, I'm telling you that in some sense, well, not in some sense, that randomness simplifies many things. So instead of some complex flow, you are guaranteed that in the limit of infinite time, each point behaves in this way with the same lambda 1, lambda 2, and lambda, and so only R and N will be different, but if you are ready to ignore the rotations, every point is going to be the same. So it's kind of remarkable simplicity, which means that in some sense, in this sense, the flow is equivalent to this matrix of which is nearly trivial, that you simply have this simple flow. Okay.
Thank you. You are right. It's true that I said W is constant, and I understand it's not constant, of course. I maybe was saying that I thought maybe the velocity field was constant because I didn't realize about this rotation. So now I realize that you remove the rotation from the eigenvalue. So I understand there is this stretching direction. I think the problem came, maybe also you start this course saying today if we had difficulties, maybe it comes from the sentence you gave last day, I don't know, that you say that a major stretching direction is independent of time. Are you removing the rotation from this, from this little n, from this major stretching direction? Or is this taking rotation into account? Because I have difficulties with this sentence that the major stretching direction is independent of time. I understood this correctly?
Well, I'm really glad that we are talking about all these things, because this way we can correct some things, and I'm quite certain that this is relevant also for others to that to another extent. So major stretching direction is a direction which all the time rotates in space. It's not that it's constant, it's independent of the past. So you take this stretching direction, it's pointing at a given point in space and time in a very definite direction. So it is independent of, it is by definition the dimension of say the direction of longest dimension of ellipsoid, which started here or maybe here, and this is trajectory which comes to this point, fluid particle trajectory. So you do not care about which time in the past this thing, so you injected this ball, okay? So this is independence which you need to grasp, because so major stretching direction is the same as first column of R, okay?
Yeah.
So it's RI1. So then if you consider this, it's not so obvious that this matrix R does not depend on the past. However, it does not, because this equation which we have for evolution of this matrix R is very specific. So here, please listen, you need to think about these things. So R is an object which lives in a kind of compact space in contrast to W, in the sense that it is an orthogonal matrix. So you can specify it with, say, Euler angles or other variables which have finite range of variation. Okay.
Yeah, I'm thinking.
Well, most simply, it's metrics which, so to say, what does orthogonality tells you? Orthogonality tells you that, say, elements of this matrix squared are bounded, okay?
Yeah.
So this is, in this sense, elements of this matrix live on a finite range. They can only take finite range of values in the corresponding space. So then when they evolve according to some matrix, and this matrix, in fact, only knows, as we learned about, so it's roughly R transpose sigma R. So very roughly, this matrix evolves as in the same way as this, okay? It's an approximation, it's not exact statement, it's only to understand things. So what will happen is that this matrix will completely change its values in the characteristic time, which is 1 over sigma. And the reason is that if you take, say, some value, so you see that here, so roughly how you estimate changes in R, you take as a model that sigma is constant. Now, this is okay if sigma is not short correlated, but let us, I don't want to concentrate on details here. So roughly the solution is this, so which tells you that within time, which is of order of 1 over sigma, which means of order of characteristic value of inverse of characteristic value of this matrix, R will change by factor of order 1. Now, factor of order 1 for R, which changes, whose whole changes happen over domain of order 1, means that it will change completely. Okay?
Yeah. Okay. So this is what you meant, independent of initial orientation and finite time variations. So this is what you mean by finite time independence.
Yes. So when I tell that you could inject ball, say 1 hour ago or 2 hours ago, and you get the same major stretch in direction, it means that this R at time of observation, which determines the major stretch in direction through this equation, will not depend on initial condition. Okay. So it forgets initial condition within time of order 1 over sigma, which is quite quick. So typically in turbulence, it forgets the initial condition within time, which is Kolmogorov time. And this also means that, in fact, to determine major stretch in direction, you need to track evolution for times of order of Kolmogorov time. Okay. Now, all right. So I would like to return to this point because you do need to understand it because it gives you a very simple understanding of what is turbulence. It's like everywhere hyperbolic, the same exponent. It's kind of equivalent to this. So sigma, which is very complex process, in this sense is equivalent to this. Now, in which sense it's true, in which sense it's not true. Now, it's true, as we saw, that you need to ignore these matrices of rotation, but you could, in some sense, also introduce some rotations in here, and that is not kind of a problem. The essential difference between this simple flow and turbulence is that, in fact, at any finite time, so this is true in the limit of infinite time. However, as you consider time which is necessarily finite, you do have some points where this behavior is wrong. And if you introduce time-dependent Lyapunov exponents, then there is a significant deviation from their infinite time values. Okay, so here I mean lambda 1 infinity in that notation which we use, infinite time limits of these finite time Lyapunov exponents. So there are some points in space for which matrix W will have lambda 1 of t and lambda 2 of t, which is very different from their infinite time limits. Now, the volume fraction of these initial points disappears exponentially, and that is this exponential. So the volume fraction disappears according to the law, which is exponential minus t times this entropy function of lambda 1, lambda 2, which simply tells you the rate of exponential decay of volumes for which Lyapunov exponents, finite time Lyapunov exponents in this matrix will be equal to λ1 and λ2. So if λ1 and λ2 are different from infinite time limits, then S is strictly positive, which means that volumes of these points decay. And this is how we understand that in the limit of infinite time, all lambdas will become equal to their infinite time versions. Okay, so I hope that this helps everybody here in the audience, more or less. So if, and I thank you for this opportunity to talk about these things. Okay.
Thank you.
All right. So let us then return to this issue of connection between. So I was showing to you that gamma of k, you would think that this is something like exponent k rho 1, which is, for instance, used in some papers. And in fact, it's not quite true. It's true with certain understanding that you consider k, which are in fact larger than -1, as I hope to show you today. So how do you see this? So the thinking here is very simple, that you have this WR, which is R lambda and R, and of course this R is W of t r at time 0. So this is, let's call it R of 0. So then you understand that this is something like R, which acts on exponent of rho 1, and then you need n R of 0, component 1. And here you have Ri1, and we are looking at ith component of this vector. Okay, so this is by definition. So here we again approximate lambda as exponent rho 1, and we neglect the contribution of all the rest because rho 1 is going to be much larger than rho 2. So there is exponential factor of difference between the different values, eigenvalues of this matrix lambda. So then this approximation is very simple. It tells you that, so this is direction, nothing but major stretching direction as we defined it. And the growth happens according to this exponent because this is some constant factor, it's a constant. So our conclusion is that from this we have that the growth of WR will be something like exponent of rho 1. So if we neglect some factors of order 1, this is the asymptotic equality. So when you use it in this equality, you understand that this must be true. Now, it is not completely true. And it's not completely true because you want to consider your gamma of k, you consider actually moments where k is any real number. Now, if k is negative, then, so it's always good when you consider some physical problems to consider limiting cases. And this is something which you always need to keep in mind. What are the limiting cases? So consider behavior when k goes to -infinity. Now, for that thing, you see immediately that you do not want events where r grows exponentially, because for negative k, events where r grows exponentially will produce exponentially small contribution into this average. And if we take limit of k going to -infinity, it will simply be negligible. On the other hand, you have some rare events where r in fact decreases exponentially. And you understand that you must have such type of events, at least for incompressibility, because if for some directions r grows, then because the total volume must be conserved. So if you start with all possible directions, which form a ball, then some directions must decrease. And this is nothing but this ellipsoid of which we spoke, that there is one dimension which is decreasing. So that dimension will produce R which exponentially decreases. And if so, it is this dimension which will actually determine gamma of k for k which is negative. Now, at this point, you can wonder if really you want this gamma of k to consider it at k which is negative. So you can say, well, okay, maybe I simply don't care about this. In fact, you do, and the reason is that the study of global properties of gamma of k allows you to get a lot of insight into other properties. So when you consider global behavior of gamma of k, which means gamma of k is a function of k, which is any real number, you will find out that in this way, it is the simplest to prove that Lyapunov exponent is positive. In this way, you can derive the third Lyapunov exponent from gamma of k. And in this way, you can actually derive correlation dimension of attractors, of which we'll speak. So considering gamma of k for any k is a very useful procedure. And I will, at this point, start connecting it with the statistics of this W to see how exponentially contracting trajectories, pairs of trajectories, actually contribute gamma of k at negative k. All right. Let us see. So we start from simply writing, okay? So we write by definition what is R of k. So this is this. So we are considering R of kt. Let's divide it by rk times 0. And this is, by definition, W at time t times initial orientation vector to power k average. Now for W, we have this decomposition, our singular value decomposition. So let's use it. Because R is rotation matrix, this is the same as average of lambda n0 to power k. So at this point, we will not make approximation that you can neglect all other lambdas besides, all other row i's besides row 1 in lambda, because we are actually interested also in contracting events. So these contracting events are of high interest because, for instance, they determine collisions of things. So if you consider two particles in turbulence which come to collision, it means that the distance between them actually decreases and not increases. And for that purpose, you want to know the probability of these events where particles where the distance is actually contracting. So it's very physical interest. It's not something which we consider only for mathematical manipulations. We will consider rates of collisions in turbulence. We will not have very much time for that, but we will consider it because it has a lot of applications. And you will see how this contracting events, and actually lambda 3 determines this type of events. So then if we don't neglect it, then modulus of this is equal to square root, well, okay, if we are considering kth moment, then this is average of exponent twice rho 1 m1 square plus exponent twice rho 2 m2 square plus exponent 2 rho 3 m3 square to power k over 2, where mi is n matrix acting on initial orientation, ith component. Okay, so this is simply, this is a quantity. We don't do any approximations. Lambda is diagonal matrix with exponents as diagonal elements. So we find this by using simple matrix multiplication. So then if we look at this equation, we realize that we need to use average procedure. So asymptotically, in the limit of large times, this is going to be equal to integral of 0, 1, 0, 2. Here we have exponent twice rho 1 and 1 square plus exponent twice rho 2 and 2 square plus exponent 2 rho 3 and 3 square to power k over 2. And here we have the probability density function of rho's, which is given by minus t as rho 1, rho 2. Here we formulate it in terms of s, which is of rho's, which are lambda of exponents times t. So we must then here put, instead of arguments themselves, we put here rho 1 over t, rho 2 over t, and finally we have this delta function, which guarantees incompressibility. Now, all the calculations which we are doing, most of them are independent of incompressibility assumption, and we will relax it in fact later. However, I do it so that we are concentrated on the properties of turbulence, which is incompressible, and motion of fluid particles. So this is our formula, and we realize that as usual in this type of situations, integral is determined by the saddle point. So integral is determined by rho I equal rho I star, which in fact depend on k. Okay, so this is in the limit of large times. This is, as usual, integral which is determined by saddle point, or the point which will give maximum. And this point is going to be proportional to time. So in fact, we can claim that this is scaling linearly with time. So you can call it lambda I of k times t. Okay, so this is our usual understanding. Only here to see it, you may consider it in this way, that in the limit of large times, each of rho i's has a linear behavior in time, so that each exponent has exponential behavior in time. So for all possible values of rho's which can occur, one of the terms will dominate this average, these brackets. We don't know a priori which of them will dominate, because we are considering k which can be negative, and that can amplify rho 2 in comparison with rho 1, or rho 3 in comparison with rho 2. So it's not obvious from the very beginning which is going to be where. However, what is obvious is that the integral is a saddle point, and this saddle point calculation, again in the leading order, will not depend on the values of M1, M2, and M3, as long as these values are not zero. So the result, exponential dependence on time. So since we are calculating gamma of k, so gamma of k will not depend on mi as long as these mi are non-zero. So I hope that this point is understood. So if they are not zero, they simply appear as pre-exponential factors in saddle point calculation. And because gamma of k is by definition exponent of growth, we do not care about this pre-exponential factor, and there will be no dependence of gamma of k on these m's. However, if one of these m's is actually zero, it will change the saddle point calculations, because one of the terms will simply not appear and we will not be able to make any optimal value calculation. All right, so this point is in fact very useful because it allows us to define gamma of k in a way which is useful for numerical simulations. So we so far defined it for some particular orientation, and we told, again, so far somewhat heuristically, that initial orientation does not matter in gamma of k. Now, this is already a proof that actually gamma of k does not depend on initial orientation. And once we have this proof, we can redefine gamma of k in a way which is to average over all initial orientations. That is, we will define gamma of k as limit of the same averaging procedure, which is, I remind, averaging over space. The only change which we will make, so I'll keep the red color here, will be that we will perform also average over initial orientation of the pair. And you may divide by 4 pi the area of unit sphere in 3 dimensions. So we introduced, besides average over space, we introduce also average over n. Now, the utility of this in numerical simulations is that in this way, you make convergence much faster. So you start to get to exponent, well, not much faster, but faster. So the fact that you can randomize initial orientation allows you kind of to scan faster the all possible values of gamma of k and have faster convergent quantity, which again for simulations it is essential. So if you kind of create artificial asymmetry, for instance, using all pairs which point in the same direction initially, you kind of create by yourself a bit an obstacle to the convergence to the limit. And here so it's not that you change a lot. You don't change in terms of time so much. However, the reason why I'm talking about this is that the quantity which you want to measure, as we talked about in one of the first lectures, was that the problem with calculation, numerical calculation of this quantity, is that it is determined by exponentially rare events in time. So you need to accumulate a lot of statistics to define it. And then every simplification which you can get can in fact be quite decisive. So please have in mind that if you want to measure generalized Lyapunov exponent, you can consider initial orientation, you can generate it randomly, and that will help in convergence of the results. So besides that, this definition is helpful numerically, it will also help us to understand the structure of gamma of k with the help of statistics of rho I. So at this point, we can rewrite gamma of k, or well, this average, which I will, okay, let me write it this way. So exponent of gamma of kt is according to this. We can write it as integral d rho 1. Well, let's see, I want somehow to make a shorthand notation, and I want to be consistent with, again, this material is found in one of the papers. Okay, so I see that there is no many ways to simplify the notation here. All right, then, okay, I will simplify things. So I will not write explicitly the averaging procedure over rows. I will keep the angular brackets. So then we can write this as angular brackets, which designate average over statistics of row 1 and row 2 and row 3. And we write it as exponent of twice row 1 mi square m1 squared plus exponent 2 row 2 m2 squared plus exponent 2 row 3 m3 squared to power k over 2. And at this point we introduce the average over angles, which I want to write in this form. It's a bit simpler to write in this way, minus m1 square minus m2 square minus m3 square, and then you have integrals over dm1, dm2, dm3. Okay, so this is the integration, a way to write this average. The reason is that why I'm writing it in this way is that you will see that it's a bit simpler because you don't need to introduce spherical coordinates. They are not, in fact, very helpful in these calculations. So now you look at these terms, and now you can get some insight into what's happening. So you understand this averaging of a sphere gives you kind of opens a way to think about which events are going to be dominated by row 1 and which by row 2 and which by row 3. So how do you understand this? You look at this and you understand that for most of the sphere of certainly this term will be the main term at large times. Now row 1 at all cannot be negative. So we have it row 1, row 2, row 3, they're arranged. And because the sum is 0, then row 1 is always a non-negative quantity. And if it is 0, then also the rest of row i's are also 0. So in this case, we have that you can simply consider that this is the largest, this prefactor is largest, and this is next, and this is next by definition because we ordered them. So there is no need to consider some kind of fluctuations where for some reason this quantity would be smaller than this because we already arranged them in a very special way. So then we can ask for which m's this term will not dominate this average, simply this term. Okay. So there are some m's whose, so if m1 is very small by itself, so you consider portion of the sphere, so if you consider it in, so small m1 means small x, which means that you consider, so if this is, let me illustrate it here. So for very small m1s, which are in fact exponentially small, so if this is unit sphere, then very small m1s means that you consider, so this is m1, so you consider something which lies almost in the plane of y and z. Okay, so if this is 1, 2, 3, so you have something which is very much like there. Okay. Well, if you can understand, so what I mean is that you're looking at area of the surface, which is like a coin. So in that case, for these very small m1s, this term, in fact, will not be dominant, and these terms will become relevant. And then you simply kind of take one by one different possibilities, and you decompose the domain into ranges where different terms are going to dominate this sum. So to decompose it, it's very useful to use what's known as decomposition of unity, where you simply write 1 in a special way, which suits the problem in consideration. So in this case, this is sum. Now I can write it in d dimensions because it's a bit so that you see that we don't really care if it's 3D or 2D or maybe high dimensional space if you consider dynamical systems. So you introduce summation in this way. So you sum from I from, well, it's, okay, let me here use the notations from the paper. So you sum n from 1 up to d, then you sum over I, which is different from L, and then you introduce step function. It's a bit tedious calculation, however, I hope that you will see that it's quite rewarding. So modulus of xl minus exponent rho I minus rho L modulus of xi. So here, theta is step function. And we want to concentrate, so theta of x is 1 if x is greater, well, let's say equals 0. Here, does the definition, step function, sometimes you need to specify what it is at 0, and it matters. In this case, it doesn't matter, so we define it as 1 at 0, and 0 for x smaller than 0. So this is the definition of step function, which if you don't know, you must know, of course. It's also sometimes called Heaviside function, which is a name which engineers sometimes use because they do need these things in the study of signals. So you have this representation of 1, which you can readily see that it is this sums to 1. And the result of all this is that you can write, using this decomposition, that exponential of gamma kt is equal to sum of n from 1 to d. So what you do is this: you introduce 1 in the integrand in this form, and you realize that each term of this sum is within the domain which is specified by step function in each term of this sum. A different term in this sum dominates the whole, the different summand dominates the sum. Okay, so you have that this is exponential of k rho L times the product I from 1 to L exponential rho L minus rho I. So it's a way to write it. In the end, it's something simple. So if you want to derive some decompositions of that sort, you simply count all possibilities, and then you will arrive at this thing. It doesn't look immediate, and I don't go into details. I will provide you with details in two-dimensional case because that's the simplest to see. So you see that if you consider 2D case, so you have only this, then this is approximately, so there is an area where M1 has the smallest of exponent of rho 2 minus rho 1. Now for this type of M1, which are smaller than this value, this sum will actually be dominated by this term, which will, because the sum of M1 square and M2 square is 1, we are on the unit sphere. In 2 dimensions, it means that we are on the unit circle. Then if M1 is so small as this, then M2 is simply 1. So you find then that this is exponent, so let me have this k. So this is exponent k rho 1, provided that M1 is larger than this small value. However, if the total contribution of this area into the integral is going to be, so this will give you simply, how to say it, so you must remember that you also integrate over the circle, so only small m1s, for small m1s this doesn't work, so integration over the circle will simply bring you the length of the circle, okay? So this will be like that, and there will be contribution of exponent k rho 2, which will come from part of the surface of the circle, which has this, which is determined by this condition. So the length which corresponds to this is simply exponent rho 2 minus rho 1. Okay. So this is what you have in this formula. All right. So let me reiterate, and then you will have understanding. So I hope so. And if you don't, please ask me. So you have this. Let me, in 2D, I can do it, in fact, with spherical angles, so that to be certain that there is understanding. So let's do it in with angles. So you have exponent 2 rho 1 cosine square of phi plus exponent 2 rho 2 sine square of phi to power k over 2 d phi, and we divide it by 2 pi, which is area. It's like 4 pi in 3-dimensional definition. So if you look at this, you see that because this term is exponentially larger than this term, unless cosine, in fact, it's a bit nicer if you take here sine and cosine. So let's define all the coordinates so that you count the angle from y-axis and not x-axis. Because it doesn't matter, I simply don't want to have pi over 2 there. Okay, so this is our integral. Now, if this phi is very small as, so for phi's which are larger than exponent of rho 2 minus rho 1, which means that these are almost all phi's, because this is a very small quantity. You simply have that this integral is exponent of k over 2, and you integrate essentially over all phi. So, so k rho 1. So there is no prefactor. Okay, so it's simply exponent k rho 1. Now for phi, the contribution of angles with phi, which is smaller or of order exponent rho 2 minus rho 1, it's going to be different, because this term will be actually of the same order as this term, because cosine for these small angles will be 1. So you will have that this integral behaves as exponent k rho 2. Cosine is 1. You neglect this term by definition. So this is a asymptotic calculation. And the integral over phi's will give you simply the measure of this phi's, which is simply exponent of rho 2 minus rho 1. And you see that this is the structure which you have here in d dimensions. Who understood or who did not understand this explanation? Okay, I can see that the board is for a long time out of focus. Nobody told me anything. So probably, Emmanuel, how did you understand if the board was out of focus?
No, the board is coming and going, but maximum out of focus is 10 seconds.
Okay.
Automatically focus often. It's true that the center of the board, it is more focused than the corner. But for example, right now I can read the
okay,
right
good
corner. It's okay.
All right, thanks. What about others? Did you understand this? It's a bit technical, however. So let us make a break of. Well, I will give you a result because we have a technical calculation, and it's good to give a result. So that you don't go disappointed that we did something lengthy and with no appreciable anything. So when you have this decomposition, you realize that it depends on K, which of them is going to dominate. Okay, so this is the whole reason why we do this, that different rho i's determine this average as it is determined. So K decides which rho i's, which of the terms of the sum will determine actually the whole sum. Okay, so when you simply compare the terms, you don't do anything more than that, you'll find a very useful result that so I'm giving it for our three-dimensional case. In the paper, you will find it for d dimensions, which you probably don't really need. So you have that gamma of K, and in the paper, in fact, it's done also with finite compressibility. So simply put sum of rho i's in all formulas to 0, and you will recover what we have on the board. So you find this, that gamma of K is actually, let me write it in the same way. So exponent of gamma of K times T is asymptotically the same as exponent K rho 1 with for K which are larger than -1. So this is the naive formula. It actually also works for negative K. However, they must be not too negative, because very large negative K, as I told you, favor events where actually there is contraction, and this rho 1 is always larger than 0, so this it doesn't describe any contractions. Then you have that for K which are between -2 and -1, it is actually a different term which determines the gamma of K, which in fact knows about rho 2 and not only rho 1. So this is average of exponent K plus 1, rho 2 minus rho 1. Okay. And then you have that for K, which is smaller than -2, you find that exponent gamma K of T is exponential of, it's very simple, average of K plus 3 times rho 3. So for negative K, which I told you that for large negative Ks, you must think about contracting events, they become the most relevant. And contracting events means rho 3, you find this. Okay. So this is our result. It's a bit, maybe it was tedious to derive, however, it gives you a connection between statistics of finite time Lyapunov exponents, which are these rho i's divided by time, and statistics of generalized Lyapunov exponent. And this is not trivial, because usually you want to know both of them for different purposes, and to have this connection allows you, for instance, to get less calculations of different quantities. So, for instance, instead of working on gamma of K for K, which is smaller than -2, which can be quite difficult, you can in fact concentrate on rho 3. And how you can concentrate on rho 3? You can concentrate on rho 3 if you simply invert the Jacobi matrix, okay? Because then it will make largest smallest and smallest largest, okay? So it gives you knowledge of these things, actually gives you all ways to make shortcuts, and shortcuts in all these calculations are highly relevant, because they could mean a lot of computational time. So despite that maybe these calculations are a bit tedious and not so self-evident, and you need to consider some details which you would not want to consider, and I realize that, the end result is quite significant. So when you want to study these things, you need, it's good if you know this. Okay, we take 15 minutes break, and then we'll continue with direct consequences of this, which are quite remarkable. Right, we continue. So this is our result which we obtained. Now it has lots of applications, and well, not lots of applications, but it has applications which I will tell you about. So for starters, you see that you can, in some sense, you can use it in order to get gamma of k for negative k, for instance. So I told you that if you want to study the statistics of rho 1 and rho 3, then you can actually use vector system of equations. And this is helpful because if you consider gamma of k with this k, okay, this is already, so you need to distinguish these values of k. So k larger than -1 means that you need typical events where actually the particles are stretched, okay? So, sorry, the distance between the particles increases, or so this is typical action of stretching by the turbulent flow. Now, this you can measure with, of course, with certain difficulty. However, that difficulty is, whatever this difficulty is, it is smaller than the difficulty when you want to measure these events, because these are no longer simple stretching events. You see it from the structure here that this is something else, and you need to think how you calculate this, because it means that when you simply consider distance between the particles, you actually want to find these events where the pair of particles did something of that sort, where the particles actually approached each other. And it's not very simple to see in numerical simulations events of this sort. So you need really to have very large pool of data in order to have this type of events. At the same time, you can write that exponential of k plus 1 rho 2 minus rho 1 is the same as exponential of k plus 1 with minus rho 1 plus rho 3 minus rho 1 average. And recall that actually you can use for rho 1 integral from 0 to t n sigma n dt prime, and for rho 3 integral from 0 to t p sigma p. So I write it here a bit differently. It's the same as to write here minus rho 3 and here minus sigma transpose. So please check that this is simply a different form. So I want you to have all sorts of forms where dn dt is sigma n minus n and sigma n, and dp dt is minus sigma transpose p plus p sigma. So I'll give you a bit different form, which is simple. So instead of studying these atypical events, which can be really difficult, you can study these. You can study these two unit vectors, which are not so atypical. There's nothing special about these vectors. They're usual events, and study this type of average. Again, it's going to be determined by ray events, but it will be here. I think so. I never actually did it, but I think so. It will be simpler to study this type of average in this formulation than to study directly the contracted events, because you would need to accumulate large number of contraction events, which is, I think, very difficult. Okay. Now, I might, of course, be wrong. And if there were people who did numerics on that in the audience, if there are some people who do it, please correct me if I'm wrong on that. However, I think that it's quite certain that it's simpler to do it in this way, which is direct usage of this relation. So let us now concentrate on another relation. Any questions on this? Yes, Joachim? Ah, no, you simply unmuted and muted. Okay, so, all right. So let us then look at the other consequence of this. So similar, of course, you can do even simpler with gamma of k for k, which is smaller than -2. You can simply study the system. So gamma of k for k, which is smaller than -2, is found by studying. So you study this. Okay? So if you want to find gamma of k for k smaller than -2, do not do it in the using direct definition. So direct definition would tell you that gamma of k is logarithm. So this is a way to train our definitions. So to remind you of our definitions and to compare the procedures. So I'm more or less here, I hope, helping you to do the simulations when the need comes. So this is the definition of gamma of k, okay? Divided by time, of course, and limit of time continuity. So this is our definition. Sigma here is matrix of velocity gradients, and n here is this. So in principle, what you need to do to find gamma of k for k smaller than -2 is to study this for k which is smaller than -2. And then you will see the problem, which will be that you need this contraction events, in fact, and they are very rare, and you would need to deal with very complex statistics. At the same time, when you consider this, you need to study a very similar system, but you don't already need to study events which are so rare in terms of this system, because in fact, k plus 3, unless you consider, say, very really negative case, which are never really needed. You study typical events from the viewpoint of this rho 3, which will be stretchings, okay? So you see that in this way, you kind of turn the problem of very complex, very rare events for k smaller than -2 into problem which is quite similar to what you had for k larger than -1 for in these terms, okay? So it's really kind of helpful to know when and how you can switch from one definition to another in terms of doing numerical simulations. It might, in fact, turn an unsurmountable a calculation which you simply cannot do into a calculation which you can do. So please have these things in mind. The next consequence is, in fact, theoretical, and also, again, it has practical implications, that if you look at this formula, you see something peculiar, that if you take k, which is -3, in fact, it gives you 0. So in the exponent, and it tells you that gamma of -3 is 0. More than that, if you take derivative of this asymptotic formula over k, so you find that this is gamma prime of k exponential gamma k of t. And on the right-hand side, you find average of rho 3 exponential of k plus 3 rho 3. And you set here k equals -3, and you use that gamma of -3 is 0. You find that gamma prime, you can show that it's no longer asymptotic quantity simply by dividing by time, and it's quite straightforward. So you find that gamma prime at -3 equals average of rho 3 at time t divided by t. So here there is factor of t, which I forgot to write. So this is where t comes here. And this is equal to lambda 3 by definition. So you find a remarkable result that if you draw gamma of k, this generalized Lyapunov exponent, it's a highly interesting object. it contains information which about growth of magnetic field or infinitesimal material lines of turbulence, and it contains information about actually all Lyapunov exponents because of incompressibility. So having generalized Lyapunov exponent, you can read off lambda 1 as slope here. So lambda 1 is gamma prime at 0. You can also, in fact, read lambda 3 because lambda 3 is gamma prime at -3. And of course, it's negative, you can see it. So then lambda 2 is simply minus lambda 1 minus lambda 3. So you get all the exponents from this plot. Then this also how you prove that first Lyapunov exponent for non-degenerate systems is in fact positive. So let us talk about this a little. So this is a proof which was done by a group of Zeldovich in 80s, where they observed this identity. So they observed it in a bit different way. So in general, gamma of minus d is 0 for incompressible flows, where d is dimension of space. So this is something which you get as they got it in a different way, which I'll show you, as I told you. However, the interesting thing here is that this is actually telling you that by studying an object for events which are rare, you get information about typical events. So gamma of minus d, as it stands, is describing rare events because it's determined by rare contractions of particles. So you take a pair of particles and you want events where they approach each other exponentially. And this is, you can see it from here, for instance. And these events actually, well, must be so that when you consider the appropriate moment of the distance, you find that it's actually conserved, okay? And at the same time, the global behavior that dictates that Lyapunov exponent of incompressible flows in non-degenerate cases must be positive. So you understand that gamma of k is a convex function, okay? This is a general conclusion which comes from Hölder inequality. So it doesn't demand anything, it's completely general. So then you know that this is a function, gamma of k, which vanishes here and vanishes here. So then the only way you can build a convex function which has two zeros is either this, well, is this, unless it is degenerate and simply is identically 0. So there is a case where gamma of k is simply 0. This would be the case of, say, many systems where there is no chaos. So in these systems, gamma, well, the trajectories will not separate and so forth. However, generally speaking, unless situation is degenerate, you find that gamma prime at 0, so this is the general shape of this function. And for this general shape of the function, because gamma prime at 0 by definition is lambda 1, that you can readily see from the definition, it is positive if there is no degeneracy. Now, this has remarkable conclusions. So, for instance, let me consider the classical mechanics. So, classical mechanics is situation where you have incompressible flow in a phase space, okay? So, incompressibility in that case is known under the name of Liouville theorem, as you all probably know. And then you understand that if you take some kind of arbitrary non-degenerate Hamiltonian, then because it describes incompressible flow, if there is no degeneracy, Lyapunov exponent must be positive, which means that a generic smooth Hamiltonian will actually produce chaos. So chaos is the general situation. Now, there are special types of Hamiltonian functions for which it will be not true because simply this will be identically zero, but they are not generic. So in some sense, what this tells is that the Hamiltonians which we typically study in courses of mechanics, which are integrable, are not non-generic and correspond to degenerate cases, and usually you have chaos in mechanical systems. So you see that for this conclusion, which is very robust, it's very not trivial. It tells you that chaos is the commonplace and not something of an exclusion, of an exception. You only need to know that gamma of k is convex and it vanishes, it has second zero at negative k. That's it. So this is the power of these arguments, where you consider a function where in some non-intuitive places, so to say, in some places which are a bit strange, because it's not typically you think of this generalized Lyapunov exponent as describing fluctuations in stretching. But this is not fluctuation, this is very strong fluctuation in stretching, it's actually contraction. And somehow this contraction includes information on typical stretching, which is λ1, because this whole thing must be, so to say, consistent in the sense that all directions must be, so to say, must know about each other, so that the total volume is conserved. Now, let me give you the other derivation of this equality, that gamma of minus d is zero, so that you can understand better what I'm telling. However, at this point, I want that you remember this plot that you can get from gamma of k all Lyapunov spectrum of turbulence, and how you can get this function that you have at this point, different ways to deal with it numerically in case that you will actually study it. And we will speak about polymers in a moment. So let me give you hopefully more understanding of how Ray events contain information on typical events because of global constraint, which is incompressibility. So you actually use an identity, which is the way in which this was derived in '84 by Zenderich, who worked on this problem in the context of growth of magnetic field, which we considered previously. So you will be able to read that work if a need comes. So you start with an identity, which I'll tell you how you derive. So identity tells you that if you consider any, for any W which has unit determinant, and of course we would want to apply it to our W. So for any W with determinant which is 1, you have that integral over unit sphere of W minus 1 n to power k dn. So I designate integral over unit sphere in this form so that you see what is integrated in this equality is equal to integral over unit sphere, let's call it n prime so that there's no confusion, of W n prime to power d plus k. So incompressibility implies this identity, and this identity actually gives you another way to derive this type of behavior of gamma of k at k equals minus d. So you see here immediately that something special happens for k equals minus d, because this becomes 0, and then this integral is in general 4 pi if we are in 3D, or simply area of unit sphere in any other dimension. And that tells you that this integral must be conserved. So the physical meaning of this is this, that if you have this unit sphere, which we fortunately have here, So you have certain transformation of Wn. So Wn, let's say for typical configuration, in this case, well, let's say it goes somewhere here, okay? So there is typical behavior of unit vectors on the which specify the orientation of pairs of infinitesimally closed trajectories, where typically these pairs separate in the same direction, which we call major stretching direction. However, at any finite time, there are also atypical vectors which will not be transformed into this same direction, and their amount must be such that the total volume enclosed by the map of all these vectors, or by the map of this unit sphere under W, must be conserved. Okay, so the volume inside is still the same, which means that you must have a sufficient amount of atypical vectors n, which will guarantee that the total volume is still the same, which is the volume of unit ball. All right, so let us implement this idea by considering it's implemented in a bit different way, not by considering the volume, but by considering actually the surface. So you consider map of unit sphere where you map n to Wn divided by modulus of Wn. Okay, so obviously this is transformation of unit sphere, and you can calculate the Jacobian of this transformation, which is quite straightforward. So let me indicate how you do it. Okay. So all right, so you have this Wn, and you can consider it as a sequence of two transformations. So Jacobians of, if you have a complex transformation, which means transformation where you take n to something, and then that something you take to another something, then Jacobians are simply multiplied, okay? So you start from considering the map from n to Wn. Now this map, whatever it is, must conserve the total volume. And then you can see that it means that, well, Wn, well, I want to do it. Okay, so you need that, so you take a unit vector and then you take surface element ds prime, and you demand that, so you consider surface element around vector n. So you build infinitesimal volume, and you consider that its transformation must keep the volume. So the change in the extension must have the property that when you multiply it with the change of surface, the total volume included is still the same volume as it was. And that gives you an identity that initial area ds dr must be equal to the finite area, which you need to multiply now as a vector with a Wn, and you can actually remove this dr. So when you do these considerations, you will actually find that this property, which I write here, that this identity gives you that the total Jacobian is in fact of this transformation is Wn to power d. Okay, and this is what gives you this identity. Okay, so I leave it as an exercise which you can read from either my paper or the old paper by Zildovich, which I think gives less details on that, but it doesn't really matter because it's kind of straightforward and you can do it. I don't want to spend more time on this. So after you consider this transformation, you simply rescale, and rescaling is of course trivial, has trivial Jacobian, which is rescaling factor to power d minus 1. Okay, so then you take the product and you get this. In some sense, we already have this. So this is where you pick one factor wn and another factor of wn to power d minus 1 you get from rescaling back to the surface. Okay, so I hope that there are no problems with this. What is then useful is that you take this identity, which is true for any w, and apply it for our w, which is a function of x and time, and average. So then immediately you see the identity that, so let me erase this. So you find immediately the identity that average of w minus 1 n to power minus d must be 1. Okay. So this is an identity which, so you simply take d equals, k equals minus d, and then you have that this integral with k equals minus d divided by area of the surface is 1. This is kind of not asymptotic but deterministic. And then you average that identity and you find that it must scale as 1. So now how do you get from this the generalized Lyapunov exponent? This is what I would like to hear from you, because to see if you kind of could follow anything of what I was telling. So how you get from this that gamma at minus d is 0? Okay, so I presume that most of you could not follow from some place, and I need to hear you where, maybe from the very beginning of this lecture, maybe later, you probably could not understand everything, but you understood some points and the results. At this point, I want us to communicate and see where the problem is. Okay, I'll wait. So how from this identity you get that gamma of minus d is 0? Okay, thank you, Pavel. So we want to get insight into this identity, which tells you that gamma of minus d is 0, because this identity is has a lot of well, has very strong implication that typical Lyapunov exponent for incompressible flow is positive, and of course it means that's the usual way we define chaos. So chaos is defined as a positive Lyapunov exponent up to some delicate points, which we don't need to consider here. So this is the reason that I would like us to understand better where it comes from. And what I'm telling you is that it comes because of that transformations of unit vectors by metrics with unit determinant cannot be arbitrary because of volume conservation. So if this n is, say, goes to some stretched direction, and most of n's goes to stretched direction, still we are able to speak about how many n's go to contracting direction, because their overall behavior must be such that the total volume inside the map of unit sphere is conserved. So action of matrix W on unit vector is constrained. Okay, if you know the action of W on every vector, it must be such that the volume is constant. Now, we do not use it directly as conservation of volume. We actually use this property in order to have an identity for transformation of unit sphere. So we take a unit sphere, we transform unit sphere where each unit vector becomes another unit vector given by this formula. Jacobian of this transformation is Wn to power d. And then simply using this transformation, this Jacobian, you find this identity, okay? So this identity is in some sense kind of trivial, okay? Well, maybe you don't see that, okay, so put in this n equals this. Then w minus 1 acts on w, modulus n gives you 1, and you're left with wn to power k in the denominator. And then another d comes from Jacobian, so you get this, okay? This is where this identity comes. Now, the question which was asked is that, okay, so if you put in this identity k equals, which is true for any k, you put k equals minus d, and then you find that w minus 1 n to power minus d integral over n divided by area of the surface of unit sphere in d dimensions, which is designated typically by s d minus 1, must be 1. Apply this identity, it's completely general. Apply it to w, which is our w, our Jacobian matrix, and average, which means you have time fixed and large, and x, which is initial point which defines Jacobian matrix, we average over initial x. So then we get this identity, okay? Because if this quantity would behave in exponential way, either growing or decreasing, we would not be able to have this identity, okay? So what the question was, how from this you see that generalized Lyapunov exponent at k equals minus d is 0. Who understood the question? Pavel, did you understand? Okay, thanks. All right, so at least some of you understand the question. Now we need to understand the answer. Okay, let me do it. I'll simplify things for you. So for derivation of this identity, it's useful to have it like this, but let me. So if W has unit determinant, then also its inverse has unit determinant. So we can in fact call W minus 1 and have this identity. So then we would find that this is true. Do you see from this that gamma of minus d is 0? Okay, we are in trouble. Yes, what is so difficult? It's definition. So our definition W tells you that asymptotically gamma Wn to power k at large times behaves as exponent gamma k of t. I simply, in the last formulation, so in the first formulation, I wanted to simply to check your vigilance that you are able to change W and W minus 1 and understand that this is completely general and you don't really use any properties of W in this identity besides unit determinant. And then I changed it with definitions. So what is, who does not understand this definition? We are working on it for quite a number of lectures, so please learn it. All right. So this, by definition, tells you that gamma of minus d is 0. Okay. Who did not understand it? All right. So then let us consider other consequence of this, which, as you can guess, you take again the derivative over k, and then after taking the derivative over k, you set k equals minus d. So what you get here, so you find after taking k to 0, you find that, taking derivative over k, you find average of dn of logarithm of w minus 1n times w minus, well, not minus 1, already we are using w, so let's keep here w. Then you have wn to power k, which we set to k equals minus d. So we have here minus d. And then we have similar derivative here, which is equal integral dn prime minus logarithm of w minus 1n prime. And that's it, because then you set k equals minus d, so this is already gives you 1. Then you average this, and you see that this is kind of, well, so by definition, if you average this, so in order to get from it useful information, you need to do it like this. Then you need to tell that this is exponent gamma kt, and then it tells you that gamma prime k equals minus d times time t is this. Now this is already something which is very similar to the third Lyapunov exponent. However, here it's a bit less obvious, because you need to switch w to w minus 1. You need then to check if singular value decomposition tells you that actually this gives you lambda 3. You can verify that it's okay, that indeed you get that this gives you lambda 3, which is that gamma prime at minus dimension of space is in fact lambda d. It's again something which works at d dimensions, which and you can reproduce this. Okay, so this was an exercise. I'll give you some more at this point. So maybe we'll take 15 minutes break and then we continue. So what I will do is, well, maybe before, let us consider from this viewpoint polymers, okay? So I remind to you that we found that probability density function of size of polymer molecules obeys a power law in the range which is r to power minus alpha minus 1, in the range of r's between the coil size and the full length of polymer molecule. And this alpha can be obtained as solution of this equation from the generalized Lyapunov exponent. So this is one of the applications of generalized Lyapunov exponent. So we considered another application, we considered the growth rate of moments. So what I would like us to do is to see what we can tell from this behavior of gamma of k about behavior of this alpha. Okay, this we will do after the break. So we take some 15 minutes break and then we continue, unless there are any questions. So was it, yes?
Yeah, it's not a question, but when you ask the question about the relation with Lyapunov, general Lyapunov, the truth is that I'm not fluent with relations, the definitions. So I was trying to search in bibliography this Jacobian to R relation, because I didn't remember very well but I couldn't find in the papers I searched. So what is the paper you are following actually? Today you opened the paper. What is the title of this paper?
So I sent you in the beginning of the course papers, maybe not all of you. I think that you could not receive it because I think there was some problem with mail.
Yeah, but they already sent me the initial emails, so it's okay.
Okay, so this is the paper from the last, from 2019, which is called quartic polynomial approximation for fluctuations. Yeah, so there you have all these details.
Yeah, it was only the relation with R, which you already jumped fastly. So.
All right.
You know well. Thank you.
All right. So we continue after the break. So you have learned quite detailed properties of the generalized Lyapunov exponent. There are more, however, these are probably the most robust. You can find in this paper, which I cited in response to Emmanuel, that, for instance, in two-dimensional case, you can show that gamma of k, which then passes through 0, in fact, is symmetric with respect to point k minus 1. So you have a much simpler structure of this function. And again, this is something which has applications. So when I speak of two dimensions, it doesn't mean that you it's something in the mind of theoretician. It's something which, for instance, you have on the surface of water, because surface flow is, so if you have flow, which is turbulent inside, and you have particles which are confined to the free surface of water, then they do have a flow. However, the confinement means that, which happens due to surface tension and other effects, means that they actually have, there is a flow of particles, which is two-dimensional. And then you can use it, and there are other applications, atmosphere, oceans. For instance, Lyapunov exponent in 2D case was studied in the case of where you consider how things are transported in the ocean. And of course, it's very relevant because it influences transport of things like phytoplankton, not phytoplankton, some sorts of plankton are passively transported by flows, and then these properties are relevant. So everything we speak about has applications, and it's despite that it might look a bit abstract knowledge, it's not. So I stressed it many times, and I'll continue with some examples. So let us, at this point, return to the problem of polymers and see whether we can tell anything about their behavior using our present understanding of the generalized Lyapunov exponent. So let me start with something which you could, in fact, do also without studying these properties, which is to study the coil stretch transition itself. So as a check that you understood anything, not anything, but that you understood this, please, so alpha, consider the situation as it's often happens in experiments. You have turbulent flow, you have polymers injected into it, and polymers occupy little volume by weight, so it's several parts per million by weight, so they don't change bulk properties of the fluid so much if they're coiled. And then you gradually increase λ1 by increasing the energy which you inject into the flow. So I remind to you that, as we saw, λ1 is something which we can estimate as by simple Kolmogorov estimate and times numerical factor. And this is quantity which depends on Reynolds number only weakly. So you can, for λ1, roughly use the Kolmogorov theory. So you increase epsilon, lambda1 increases, and at a certain point, polymers, you see that suddenly there is a new macroscopic degree of freedom in the flow, which so the turbulence becomes actually elastic, and polymers are stretched. So let us study the vicinity of this transition. And what I would like to request you is to tell me when, so this alpha depends on lambda1, or in fact on statistics of gradients of turbulence through this generalized Lyapunov exponent. It solves this. So when, in terms of alpha, the coil stretch transition happens. Okay, that's what I figured. All right, so what do you think? All right, let me, before I help you in answering this, let me wait a little. Maybe you will be able to tell me what's happening. So what is this? So let me start from simpler question. So if I tell you that polymers, you are given that polymers are most of the time in the coil state, what can you tell about alpha in this law, which you have on the board?
Alpha is greater than 0.
Yes, thank you. Who told this?
Me, Nathan.
Okay, Nathan, thank you. All right, so can you explain to others? Because I think that maybe others don't understand. Please.
I remember it from the distribution of the how do I put it? The distance between two particles. So that probability distribution is an exponential function which depends on alpha, and so if alpha is positive, it means that most of the times the so it's actually an exponential decay, which means that your most of the time the polymer is in a coiled state. So if I'm explaining it correctly.
Yes, you are referring to the probability density function of rho, which was logarithm of the size, which is indeed exponential. So, however, what I would like that you or somebody else will see is this. So how do you, so this is the behavior which you have in terms of R, you don't have exponential, it's a power law. That's, of course, it's simply in logarithmic variable, it's exponential. So you have this picture. How can you claim that polymer is most of the time coiled? This is not a trivial question, okay? So if you cannot answer it immediately or cannot answer it at all, it's okay. It's not, what I want is kind of to stimulate your thinking, which is something which I think is necessary. So my question, if it was not understood, is this. You know that, say, probability density function has this shape. Okay. Now, this shape is consistent with both sides of alpha. Okay. So if you take, say, alpha, which is negative, but by absolute value smaller than 1, then this is still decaying function like this. Okay. So how do you decide from, so from this shape only, you cannot really, I'm telling you this, that you cannot decide if you would have most of the time polymers stretched or coiled. Okay, so you may have decay and yet things can be coiled or stretched. So how do you understand this? Okay, let us go to the meaning of probability. So what is the meaning of probability if you consider one polymer molecule? What does it mean most of the time coiled or most of the time stretched? Well, this is so Pavel proposes that we can decide this thing by considering the maximum of the PDF. This is this thing which I told you that is not working because you can have this situation where take alpha, which is say minus 0.1, okay? So this will be r to power minus 0.9. It will be decaying, the maximum will be here, and yet I'm claiming that the polymer will be stretched most of the time. Okay. So yes, so this way of thinking is actually, which you're proposing, would work if we would work with logarithmic variable. And I, on purpose, ask it in terms of directly available probabilities. That's the function of size, which people measure in experiments, since I want you to understand something. Okay, so Pavel is perplexed about my claim that if you take, say, alpha, which is minus 0.1, polymers are stretched most of the time. Okay, most of the time. Now, Newton would not have a problem with this probably, because he would think about probability distribution function of logarithmic variable, in terms of which we originally derived this result. And probability density function of rho is exponential of minus alpha rho. So of course, if alpha is minus 0.1, this is positive, it grows. So by the same logic which Pavel wants to use here, this would be something growing toward large rho, which would mean that polymer is stretched most of the time. So where is the truth here? Think. It's pleasant. So Pavel, when you tell okay, what does that mean?
Hello.
Yes, hello.
Yeah, probably yes. It will be stretched since the PDF is exponent in the positive power.
Well, yes, this is the answer.
That's okay.
However, it doesn't explain anything, because what I'm telling you is that with your logic, if you used your logic here, you would tell in this case, because this is decaying, it has maximum here, you would tell that polymers are coiled most of the time. If you apply the same logic to logarithmic variable, you would tell that they are stretched most of the time. So the implication is that this logic is not really good logic, okay? Because it can bring you wrong results. Simply looking at maximum of the PDF can be wrong.
Okay, I understood.
Okay, so Francesco proposes that variance must be finite. This is a step toward the good direction, thanks. However, it's yet too restrictive because, for instance, if you consider a situation where, say, alpha equals 1, okay? So polymers will be, for alpha equals 1, the tail will be R2 minus 2, and its variance would be infinite, and yet polymers would be coiled most of the time. So variance will not help. Okay. Other ideas? All right. maybe you can think of a quantity which is somewhat more fundamental than variance. So when you consider probability density function, actually, this is something which is kind of you do need to know. So you want to know, say for polymer, okay, you want to know what is typical size, in a sense, what is the size where you will find it most of the time. This means that, say, you have polymer in the flow, you look at arbitrary time, and with overwhelming probability, it is either coiled or stretched. Or equivalently, you follow the polymer all the time, and you find that the largest fraction of time it was coiled. Okay, these are the same things. So how do you decide it from the mathematical formula? What is, so maximum is not working. This is what I'm telling you by this example, where you can see that simply by passage of variables, what was maximum becomes in fact minimum. Okay, so this is not a good quantity. So what is a good quantity? All right, so this is, so by definition, so I think that maybe you never had a chance to really think about definitions of probability and what it tells. So maybe you did. So if you consider P of R, by definition, this is fraction of time which polymer spent with lengths. So P of R dr, this is probability to have R in the interval from R to R plus dr. Now this is equal, using operational definition of probability, to integral over time of step function of R of t minus R. So this step function guarantees that R at time t is larger than R. However, at the same time, we want it to be smaller than R plus dr. So we multiply it with another step function, R of t. Then by definition, this is fraction of time of a large time interval designated by t capital that polymer spent with size between R and R plus dr. Who agrees with, well, who does not understand that this is the definition of probability if you work with one polymer? So for instance, you generate your matrix of velocity gradients for very long times. You have very large piece of trajectory, which length is t capital. So then, using our equation of motion, which was the full equation of motion was dr dt is sigma r minus r tau 1 minus r square over h square, and you also introduce thermal noise so that there is a coil state. So this is our, so you solve this full equation of state, equation of motion. So you find R as a function of time, and then from that R as a function of time, you can evaluate the probability in this way. Okay. And if time interval is large enough, then this probability will not depend on the value of t capital, and this would be really probability. Okay, so I hope that there is no problem with this operational definition of probability distribution function. So then, how do you decide about, so how do you get from here P of R? So, okay, you need somehow to divide by R, and you can do it, and you can use our definition with deltas. So what does it kind of tell you? Okay, so it tells, this equality tells you something about what really has the meaning. Oh, okay. All right, so you unfortunately do not see this, so let me help you with that. So you see that the true quantity, which tells you the actual physical quantity, which is fraction of time that polymer was in this size. And why I call it physical quantity? Because it does not depend on choice of variables. So I told you before that whenever you want to understand something about probability, you need to think not about, well, it's usually good to think not about probability density, but about really probability. So this is really probability that R is in this interval. And then if you switch to logarithmic variable, nothing really changes, simply the label, but you are in the same interval, okay? So you see from this identity that what has true physical meaning is P of R times dr. That is integral of probability density function. In other words, if you want to know if the polymer is coiled most of the time, you need to decide whether this integral from 0 up to some R0, P of R dr, where R0 is larger than R coil, whether this integral is going to be close to 1. If you find that this integral is close to 1, then by definition here, it tells you that most of the time, a fraction of time which is close to 1, polymer was in a coiled state. In contrast, if you find that this quantity is small, it's the other way around. Most of the time it was not coiled, and if it was not coiled, the only other possibility is that it was stretched. Okay, so if you want to decide how things look physically in space with real polymers, you need to consider not probability density function, but its integral. So in this case, if you take alpha, which is minus 0.1, probability density functions still have the maximum at the size of the coil. However, when you integrate it over R, this integral is going to diverge. So something which decays with R still can have divergent integral. So R to power minus 0.9 has infinite integral if you don't cut it off at some finite length of the polymer molecule. So this is something which I really want you to bear in mind, that you care not about the maximum of probability, you care about what determines the normalization. So we call the range of random variable, for which if you integrate over this range, you get quantity which is close to 1. We call this range kind of the bulk of probability, okay? Typical name, or main events. There are different names you'll see in literature. So you do need to know these things because this is the physics of probability. This is what it means, okay? All right, so our decision if the polymer is coiled or stretched is by the sign of alpha, not because of the maximum of the probability, but because of what determines the normalization interval. If alpha is larger than 0, it means the integral at large r's is convergent, which means that polymer is coiled. If alpha is smaller than 0, then the integral at large r is divergent, which means that polymer is most of the time stretched. Okay, is it understood at this point?
Yes, much better. But is this R with the log applied? So no, I see now. Rho. Okay. I understood. It's okay.
Okay, so I see that some people are leaving because they're probably frustrated because of all these things. I apologize for that. Please, those who stay, ask more questions, because I don't see any point of studying some advanced physics or advanced mathematics if you do not think about these things. You do not ask yourself what it is that we are writing on the board, what are these probability density functions, because they have immediate physical meaning. And you need to have it in mind in order simply to have meaningful activity in physics. Okay, so this is why I spend time on these things. So then we want to know, to describe the closed stretch transition, we need to decide when alpha, which depends, which is determined by properties of turbulence through the generalized Lyapunov exponent, when it is going to be 0. Okay, so how do you do it? It's quite usual technique. So you want to study kind of phase transition. So you want to consider vicinity of that transition. That is, you look at the situation where alpha, which solves this equation, is actually a small number. All right. So if alpha is small, then we can use our cumulative expansion theorem, which you probably forgot. I simply remind you, the leading order term is alpha lambda 1, which is what you also have here. So the derivative at 0 is lambda 1. And then there is next order term, which is alpha squared delta over 2, where delta is dispersion of logarithmic stretching rate of distances, which we wrote as m sigma m at 0 minus lambda 1 m sigma m at time t minus lambda 1 average dt. And then I remind you, I told you that you need to take n in the steady state. And at this point of the course, you already understand what the steady state means. It means that you need to use here for n major stretching direction. And if you understand n in this way, then you don't need to specify anything, you simply average, okay? So this is delta. And what we saw about these quantities was that if you consider dependence of lambda 1 on Reynolds number, it's very weak, it's negligible. Well, roughly it's negligible. However, if you consider dependence times Kolmogorov time of delta on the Reynolds number, delta also has dimensions of inverse time, then you have delta times tau k, which behaves as Reynolds to power something like 0.3. And now I give you, we already spoke about this, that in this way you can, by changing intermittency of turbulence at the fixed value of epsilon of average energy dissipation, which effectively means that you have fixed value of lambda 1, because lambda 1 with a good approximation is describable by Kolmogorov theory. It is inverse Kolmogorov time up to some non-trivial constant. So at this point, we can actually figure out how intermittency does it in detail. So for that, what you need to do is to solve this equation with this alpha. And of course, you need to make certain that you do not need higher order terms. So for alpha, there is, of course, trivial solution of this equation, which is alpha equals 0. So we want a non-trivial 0. And non-trivial 0 is found by equating alpha lambda 1 plus alpha squared delta over 2 equals alpha over tau. So because we are looking for non-trivial solution, then we can divide by alpha. So alpha is not 0. And here we have 1. And then we are left with simple equation, which gives us that alpha is approximately 2 over delta, 1 over tau minus lambda 1. So this allows you to be certain that lambda 1 equals 1 over tau is the transition. So there is no way that any intermittency would change that criterion, because you see from this that alpha, which is small, implies that alpha is proportional to 1 over tau minus lambda 1 and has the same sign as 1 over tau minus lambda 1, because dispersion is always a positive quantity. Okay, strictly speaking, non-negative, but here it's positive. So, because there are fluctuations. So you see that alpha is greater than 0 if λ1 is smaller than 1 over tau, and this is coiled state as we discussed previously. And alpha is smaller than 0 if λ1 is greater than 1 over tau. This is stretch state, as we also discussed previously. And you also have, could it be that I wrote this in fact to you? If I did write it, please tell me, because this I certainly wrote to you, but I don't think, I think that I didn't write you this. So this has this behavior of Reynolds number. So alpha is dimensionless quantity. So if you multiply it with tau k here, tau k here, and tau k here, this is of course the same thing, and you use this law, you find that it behaves as Reynolds to power minus 0.3 times tau k over tau minus something which is 0.114. Okay. So this gives you a very concrete criterion that in turbulence, your knowledge of present numbers tells you that coil stretch transition must happen at tau, which ratio to tau k is such that tau equals 0.114 tau k. Okay, so this is very concrete prediction. I think that it was not checked because when people checked coil stretch transition, they were not using the result, this result, that λ1 tau k is, so the result that λ1 tau k is approximately 0.114. I think it was not used. So this is something which still can be checked, and it would be, of course, useful to do. The other thing which you see from here is that if you keep Kolmogorov time constant, which means that you keep the energy injected per unit time per unit volume as a constant, and you simply increase Reynolds number, alpha will go to 0 and you can get the transition. So this is this very concrete statement which I told you before, that increase of intermittency can cause coil stretch transition without changing any energy which you inject into the flow, which is quite a spectacular phenomenon. So that we talked about. At this point, let us consider the other limits. So let us consider the situation where polymers are actually stretched. So we are above the coil stretch transition. λ1 is larger than 1 over tau. And then you consider what you can tell from the knowledge of this function. Well, it's a bit you can see something here that if you take, excuse me. You might think how you use the fact that, so for above coil stretch transition, alpha is negative, and you want to use the fact that gamma at -3 is, P of R, one moment. Yes, so how do I get this law? Okay, so you need to get that P of R, this is explained in the paper, in another paper which you have on synchronization of polymers, that actually at large values of λ1 times tau, when you are well in the limit of very strong flow, well above the stretch state, you get that P of R at small r's in this, they still have meaning. So in this situation, if you are above coil stretch state, the probability density function has this form. So at coil state, there is not much. Everything is concentrated at a fully stretched molecule. up to these acts of when it's torn by the flow. And here you still have this law. So I want you to understand that this law doesn't really know if polymer is stretched or coiled, because our derivation was completely local. We provided this stationarity condition in this interval, which is kind of asymptotic interval, and we found that there the solution must be this power law, and this solution does not really know about whether polymer is coiled or stretched, and it works both below the coil stretch transition and above the coil stretch transition. So somehow this alpha equals minus d must appear here, but I see in this equation that somehow this becomes 0 and this becomes minus d over tau. Ah, okay, this is okay. So, all right. So, limit of, you consider the limit where tau goes kind of to infinity, okay? So, tau goes to infinity means that 1 over tau goes to 0. So, it's one of the ways in which you can then show this in more intelligent form, considering dimensionless quantities. But going to limit of very well above the stretch transition corresponds, as you can see from here, to limit where tau goes to infinity, because then this any lambda 1 will be above, well above 0, okay? So then in this limit, you see that this goes to 0 and alpha must go to minus d. And you can actually prove it in a bit more intelligent way, but equivalent, that if you consider, you can again do the perturbation theory. Let me do it, in fact, and to show that alpha goes to d. So how do you deal with this? So this is where we use this property. So this is the limit which in this paper which you have is called limit of threads. Because this is simply meaning that elasticity becomes negligible, and you are dealing simply with objects which are kind of, well, it's like really a thread. You can stretch it and nothing objects the stretching until you get it to the full length, okay? This is why we call it in this way. So zero elasticity, and all objects are most of the time stretched. However, despite that these objects are most of the time stretched, they will perform these fluctuations to small r's. So if you really think about injecting a small thread inside a turbulent flow, it will be stretched. So you consider its size much smaller than the viscous scale. However, there will be always fluctuations and it will not be constantly stretched. So from time to time, it will get into a region where the flow will be very kind of will be contracting or not stretching at all. And due to this occurrence in these flows, this thread will actually contract and will not be, so the contraction events will cause the thread to become small and not stretched, okay? So you can describe the probability of this. So if you want to describe what's the probability to have size of this thread given by r, which is much smaller than the length of the thread, you will find that this is given by this simple geometric factor. So you can see that this is simply r to power dimensional space minus 1, which is volume of a spherical shell, okay? So you understand from this that it's becoming a completely geometric property of any object. And then you can do actually perturbation theory. So you look for alpha as d. So in the limit, alpha must become minus d. So you look for alpha in this form, minus d plus lambda. So then you have here gamma of minus d plus, plus delta equals minus d over tau plus delta over tau. And then you use these laws. So gamma at minus d is 0. And that tells you that delta times gamma prime at minus d, which is lambda 3, which is negative quantity, equals minus d over tau plus delta over tau. Now, because you can see the limit where lambda 3 tau becomes infinite, so we can see the limit where it's large. So this is the limit of tau going to infinity. So this is what I told you, that there's a way to do it intelligently in terms of dimensionless quantities. So you can then neglect this term, and you find that delta equals minus dimension of space, which in our case is 3, times lambda 3 tau. So our conclusion is that in the limit of weakly elastic polymers, probability density function to have a polymer which is much smaller than the full size is given by this law, that this is delta, which is positive, so it's minus d minus d over lambda 3 over tau and minus 1. Okay. So lambda 3 is negative quantity, which is telling you that this is the same as d over modulus lambda 3 tau, which then you put into this law and you find this minus 1. Okay, so this is describing you the opposite limit. So there is limit of very stretched polymers where elasticity is weak, and in this limit you would have this situation. Yes.
Sorry, I didn't follow you in this this perturbation thing. I don't understand even the point in this perturbation analysis. So I don't know if it's worth to start again, or I don't know how can I understand this.
Okay.
What is the point to start for starters? What are you studying here?
The point, what am I studying here?
Yeah, sorry.
Okay. No, it's not a tough question. I'm studying the situation.
Tough question to make.
Okay, so I'm studying the asymptotic situation where polymer is weakly elastic, okay?
Mm-hmm.
So what this tells you is that this tau in some sense goes to infinity because rigidity is inverse of tau.
Yeah.
So this means that you put, if you speak of one polymer inside a turbulent flow, it can be anything. It can be any value of lambda 1 times tau, okay?
Mm-hmm. Mm-hmm.
So if lambda 1 times tau is smaller than 1, then the polymer is coiled. If lambda 1 is tau is, so we sometimes call this number Weisenberg number. So Weisenberg number is, well, still, since we're talking about polymer solutions, then you will often see that Weisenberg number is defined in this way, times tau, or in other words, tau over Kolmogorov time. Now, this is not really a good definition because, as you can see from here, so Weisenberg number is a number which you devise so that it describes to you the relevance of polymers inside turbulent flow. However, this is not the parameter which decides. The parameter which really decides, the more relevant definition is lambda 1 tau. Then you can tell that for Weisenberg numbers which are smaller than 1, you have a coil, and for Weisenberg number larger than 1, you have straight state.
Mm-hmm.
And if you use this number, you would be order of magnitude wrong. This is why I'm telling that this is wrong definition, because there is factor of 0.1 between difference between these two definitions. So once you accept this definition, you can consider different limiting cases with one polymer in the flow. So I want to consider the limit of large Weisenberg number, where the flow actually stretches the polymers very strongly, and they behave effectively as kind of threads, which means that you have something like this, which doesn't resist any stretching until it's fully stretched, okay?
Yeah.
So in that case, you can still speak of fluctuations which bring you to small values of r. So if this is full length, you can still have fluctuations where r becomes much smaller than n. And the reason for these fluctuations are these contracting events that from time to time, this thread will not be stretched, but it will be actually contracted, and it will go to size which is much smaller than its full length. And our general theory is still working there. And I want to describe the behavior, the probability density function of observing a thread at this size. And what I showed to you by this perturbative analysis is that this is in the limit of threads, this is simply r to d minus 1, which is volume of spherical shell. And you can find the correction and finite elasticity, which thanks to our understanding of behavior of gamma of k, we can write explicitly in this form. Okay.
Okay, there I have a question, sorry. When you apply this gamma at -3, I thought it was the derivative. Yeah. So in the first line on the left, you replaced gamma minus d plus delta, and in the next line you have delta lambda 3. But I thought this would be 0 actually, not -3.
Well, you do Taylor expansion of this quantity at small delta. So this is gamma at minus d plus delta gamma prime at minus d. Okay.
Okay. Yes. Fine.
All right. Other questions? All right. So this is the derivation of this result. And then you want to know how relevant it is. In fact, it is relevant if you have a small number of polymer molecules, you will get into these situations depending on the flow. However, often the situation in which we are most interested is when polymer amount of polymers is such that actually they start influencing the flow. So if polymers influence the flow, you often see that they never can get fully stretched, or in fact that they can, but you don't have the interval to observe this flow. So well, I can say that the largest problem about this theory of elasticity, which is certainly a good first step toward understanding of behavior of polymers and turbulence, is that in reality you do not, so this we used already, so we do not have this interval where actually you can have R, which is much larger than coil size and much smaller than L. So this would demand that the existence of such interval would demand that L over R coil is at least 10 to power 2. And this is something which never occurs in practice. So in practice, typically this ratio is of order 10. So you cannot really have this interval. And you need to think about something else, okay? So to think of something else means to try to get some insight into the nonlinear elasticity of polymer molecule and still make an effort to solve things. So after the break of 15 minutes, I'll tell you how this can be done, and then we will finish for today. Please write me in the chat or ask me, because I see that today the amount of participants is smaller than usual. All right, we continue. So as I told you, the main problem with application of these theories is that we might not have this interval at all, and then you need to do something else. In fact, there is a way to describe the range where you do not have 2 orders of magnitude difference between these two scales. We will talk about it hopefully tomorrow. Today, I would like to start introducing the equations which describe interaction between polymers and turbulence. which is of course where the most interest in this solution in these solutions holds, because we want in the end maybe to just, yes.
Sorry, I think you have a question in the chat. I don't know if you answered already.
Yes, yes, it's true. It's okay. Pavel, this refers to your question. Yes, you read it correctly. All right, so there are somewhat different ways to derive these equations, which I'm going to show. However, I want to show that in the language which I find most physically appealing, which might be not the most rigorous, but certainly the most insightful. So what we are going to consider is interaction of polymers and turbulence. And here, unfortunately, the main difficulty with this is that if the problem of single polymer in the flow is one particle problem, interaction is by definition a collective phenomenon. And in order to describe it, you need fields and not scalar degrees of freedom. And of course, then things get much more complicated. However, that's the only way I can think about. In fact, there is something which I would like you to think, that you might be able to describe, at least numerically, it seems that it's better to describe polymers, interaction of polymers with turbulence, not with the help of fields, but with the help of actually the same polymer molecule. So I'll show to you this in a moment. So we consider polymer in the flow. I will, for simplicity, assume that we still have this interval, so that you can speak of this thing. And the reason why I assume this, despite that we do not have this in nature, is that it's certainly a good model, and it's a good approach to the problem to start from having this interval and only then see what happens when this interval of 2 orders of magnitude or more between full length and coil size, when it shrinks. So this is quite obvious that this approach must be taken, at least from the viewpoint of theory. So we have many polymers in the flow. They are all kind of randomly, their configurations are random and independent. So there is no local correlations. And then we consider the situation where they're stretched. That tells you that, like in synchronous swimming, they all do this, because we assume that they are well below the Kolmogorov scale. So they are, of course, a little bit different, but their end-to-end distance is approximately the same, points in the same direction. Okay?
Hi, Itzhak.
Yes.
Can you explain again why we don't have that condition that you wrote on top in nature? Why is that doesn't happen? Sorry, I'm missing something. I also don't see very well the equation itself, but I don't know if it's maybe my connection or the marker.
Okay, so regarding the focus, I think yes, okay. So you do not have that because, so I remind you that random walk arguments show to you that R coil is of order of square root of number of monomers, where I neglect the correction because of that random walk is self-avoiding. We discussed that, and length goes as n. Okay. In other words, the ratio goes as square root of n.
Mm-hmm.
So if you want this thing to be 10 to the power 2, which is what you need at least to have these 2 orders of magnitude greater or equal. So to have this possibility of having R between to have strong inequality here. So this means that n must be larger or equal 10 to the power 4. Now, then you can still be wondering why we cannot have n which is order 10 to the power 4. In fact, we can. So I do not have very good answer to your question. I can simply tell you that experimentalists tell me that you cannot have this interval. Real polymers never have 2 orders of magnitude difference. So this probably means that this model is a bit not so good. So you cannot have 10 to the power 5, that's for certain. But 10 to the power 4 seems to be realizable. So it could be that experimentalists have in mind the polymers which they're usually using, where n is something like 10 to the power 3, I think. And then, yes, it doesn't work. You do not have the necessary gap of sizes. However, I would think that if you really want that, you can get n to the power 10 to the power 4, n which is over the 10 to the power 4, and produce the corresponding solution. So I would think that it's the problem of polymers which are typically used in these studies. So in the labs, people don't use some fancy polymers. They order the usual things. They do not request that some people manufacture some good solution. So typically polymers are polydispersed. So you never have fixed n.
Yeah.
So they could, in fact, require the manufacturers, please produce for us n's which are order 10 to the power 4, and we will work with those. They do not do it, I think, because polymers at any rate are going to degrade soon. So it's kind of maybe not, well, I do not, as you can hear, I think that from the viewpoint of studies of interaction of polymers and turbulence, it would be good if somebody would do experiment with this order of magnitude number of monomers. However, when you speak of drag reduction, it seems that they work with monomers which are not in this range, and then you do not have this, and yet there is strong effect, and you want to explain it. So it's not. Okay, I told it. This.
Yeah, I don't know. I was just thinking about the example of ultra high molecular weight polyethylene, where you have normally on the order of 10 to the 5 monomers into a chain. I don't know if there is some.
Well, you need also that polymers can be dissolved very effectively in the flow.
Yeah, that I will have to look it up if that's the case for. I don't know them. Yeah. Okay. Just curious. Okay.
Yes, I think it's really good we talk of this, and if you, well, I understand that you work in theoretical rheology, not in experimental laboratory. However, if you know somebody who would be interested, I think it would be, as you say, it would be curious to see what happens in these solutions, because they would probably realize this theory which I'm talking about, and that would be interesting, definitely. So, and maybe
yeah, I work with numerical simulations now, but I have some background experience from back in my PhD from experimental work. So that's why I was curious if there was some, some fundamental explanation why it's just impossible to achieve that if there is some fundamental that was missing to explain why it's not possible to realize it, I guess, but it doesn't seem so. Maybe the practical realization is just not worth it for an experimental point of view or something. I don't know. Okay, thanks for your answer.
You're welcome. So this is indeed practical, and the reason why it would be good to have at least one experiment with that would be that this is the optimal conditions for drag reduction. So we would be able at least to know what is the maximal amount we can reduce, and should it turn out to be so large that it would be worth to produce such dissolvable large polymers, I think it would be good. So nobody ever did it. As far as I know, nobody had the purpose of getting polymers which allow for this range, which doesn't mean that it's irrelevant. It simply means that experimentalists do think about these things in a way which they don't. The theory is the last thing they care about until they need to process the data and decide what it means. So I hope that some of you will ever have a contact with an experimentalist and maybe mention that, and maybe it will work out. So when the polymers are, when we can assume the existence of this range, the polymers are stretched as in the synchronous swimming, which you can see on TV. And that looks quite nicely. And it also tells you that you can describe these things with fields. So you can actually introduce the field of local orientation of polymers, which is more or less the major stretching direction, which you weigh locally. So it's roughly, you average over the volume, some small volume around that point, all polymers which are inside that. So in fact, you can simply sum over small volume, but let's do it in this way. So then if you define it in this way, the lengths of all polymer molecules are a bit different. So the polymers are polydispersed, and there is no reason why they would start from the same length. So it will be somewhat different. However, their direction would be the same. So this is the major stretching direction. This is the reason we can introduce that. And then these polymers will start interacting with the flow, because each of them, so one polymer cannot do much. So one polymer, if it is stretched, it's stretched, it cannot change the flow, okay? In some sense, from the viewpoint of one polymer, to understand this, you can think in this way. So one polymer is effectively in the flow, which is linear at large scales. So here I assume that the size of the polymer molecule, despite that it is stretched, is still much smaller than viscous range. So we still have it somewhere here. So then the flow effectively is linear, as we discussed, and linear flow at infinity has infinite energy. So polymer simply cannot withstand infinite energy, and it's going to be stretched until it simply reaches the full length, which is when nonlinear elasticity will stop the stretching, or it will simply get torn, or it will stop stretching and get torn after some while. So this is what will happen with this molecule. However, if there are nearby other polymers, they will start combining their efforts, and then they can already have bulk effect. And this is what happens in drag reduction phenomenon, that they start interacting, combining their forces, and eventually they can stop the stretching by the flow. And in this case, the law by which they stop is very simple. Well, it's not simple, but it's something which is already known in physics. So to explain this thing, you need to think about stress tensor. Typically, it's designated by pi ik. Let me use another. Okay, so you have the Navier-Stokes equations, which I write immediately in incompressible case. By the way, here I want to tell something more. People did consider the possibility that polymer is stretched to size which is larger than Kolmogorov scale, and then it stopped simply because the flow starts to grow slower with the distance between the ends of the polymer molecule than the elasticity. So elasticity remains linear, and the flow grows by Kolmogorov, roughly by Kolmogorov law, r to the power 1/3. and then elasticity will stop the growth. However, it seems that this possibility is not realized in nature. Again, it might be interesting to look at because you can realize it in the lab. I don't see any problem with that. In principle, you would need to use some flow with fluid with low viscosity, which I think can be done, so that viscous scale is very small and you can have that situation. I simply cannot tell you if that situation will bring some physical phenomena so strong that they will be worth pursuing. Maybe yes, maybe no. So we consider Navier-Stokes equations, which in a general form is the law of conservation of momentum, local conservation law of momentum, where sigma ik, as you know very well, it is minus P delta ik, the contribution of pressure. Then you have the contribution which comes from, well, we put density to 1. So there's a contribution which comes from inertial transport of momentum. So this is density of momentum times the velocity at which it's transported, very simple quantity. Then you have the contribution of viscosity, which is dvi dsk plus dvk dxi. And then in general, you can introduce the correction to this, which is stress tensor due to polymers. This all agrees completely with our usual understanding of separation into macroscopic and microscopic degrees of freedom. So I remind to you, or tell to those who did not study this, that our usual thinking about fluids is that there is some macroscopic time scale, which is the time scale which is imposed by external conditions. So in the case of Kolmogorov of turbulence, the smallest time scale, if we neglect intermittency, is the Kolmogorov time. Okay, and then there are time scales of relaxation to local thermal equilibrium of all microscopic degrees of freedom. Okay, so if local relaxation time is much smaller than tau k, then the usual wisdom tells us that it's going to be something which is describable as Newtonian fluid, because all degrees of freedom are much faster than the macroscopic degrees of freedom, and they can be summarized into this local value of viscosity and maybe pressure. So this is the usual thinking. And should we have a situation where relaxation time is comparable with tau k, then there is a degree of freedom which is, so if there's some microscopic process whose time scale is comparable with Kolmogorov time, then we cannot treat it using some effective viscosity. We need to treat it as a macroscopic degree of freedom, which is described by its own macroscopic field, simply because we no longer have time separation. And in fact, this is what coil stretch transition happens to tell us. So if you look at lambda 1 tau, so if you look at tau as relaxation time, then coil stretch transition tells us that only under this condition, you might need to include the polymer degree of freedom as macroscopic field, as macroscopic degree of freedom. And this agrees with this general understanding, up to the fact that it's not order of magnitude, it's simply here equality. Okay, so this is the reason why we must include this new degree of freedom. How we describe this degree of freedom? This is in the approximation of elastic linear elasticity. You can readily see that it becomes quite simple. So typically the calculation which you do, you can find it in the book by Bird, Armstrong, and Curtis, or you can, there's no necessity for you to go into that book because you can actually fix it from general considerations. However, the physics behind it is that you consider, so I remind you, this law tells you that time derivative of momentum, which is contained, so density is 1, so momentum is simply the velocity, time derivative of momentum contained in some volume V equals, using Gauss theorem, you have that this is d sigma ik dxk dv, which is integral of sigma ik dsk over the surface of this volume. So we would like to know how polymers exert force on the on this volume V from outside. Okay. All right. So for that, you take some polymer and you think that it crosses the boundary of this volume. So this is what causes actually stress between outside and inside. So polymer wants to contract, and this imposes a force on this volume, which, for instance, can mean that it is elastic. One moment, I need to open the door. One moment, please. Hello? Yes. Okay, excuse me, home office. All right, so yes.
Sorry, can you solve the bottom line of the board? It's out of camera, the scope of the camera. We cannot see bottom line. Can you solve it, please? Thank you.
Okay. Yes, there's some light, so let me see if I can fix it in this. Okay, I think it's good. All right. So stress tensor is telling you how the exchange of momentum of some volume inside the fluid occurs with the outside fluid, and polymers actually endow every fluid element with its own elasticity, and this is describable with this PIK, and in this case it can be simply fixed as some quantity which is proportional to the concentration of polymers. So we assume that polymers are dilute. This assumption does hold in drag reduction experiments. So you can simply sum the forces. This is what this proportionality to their local concentration N means. Then you have simply Ri, Rk, which tells you that because you have elasticity which is linear, if polymer is directed like Ri, then the force is simply projection is also in the same direction, and you need kind of to project this in this way. So you need to know, so to say, how many polymers cross the surface, and this is all included. You can check with detailed calculations. And finally, you need to introduce some elasticity constant, which would tell you how given simply it would be related to tau. It would describe how rigidity of polymers, elasticity of polymers determines the stress tensor. So this is, fortunately, we don't really care about both N and kappa because they are kind of constants, and this you will see, they simply disappear from equations. So they disappear up to the assumptions which I will make. So once you write this, you get some regime, which is what we studied in the original papers on turbulence and dilute polymer solutions from a long time ago, which were then maybe at least among the first attempts to do this. So you consider the equation on this R. So you must turn R into a vector, into a field, and then instead of, so you have the usual equation in this range is sigma R minus R over tau. So what do you mean here? You mean this, that we want this range where R is between the coil size and between the full length. Now there is a possibility, and the focus is gone. Okay, so there is a possibility that polymers will combine their forces in such a way that they will actually stop stretching because they start reacting on the flow, and this will happen at characteristic size, which we called R back reaction and designated in this way, where this size, where polymers will stop because stretching because of their interaction with the flow, will still be inside this range between the size of the coil and the full length of the polymer molecule. Okay, so this is a possibility which can occur provided you pick this concentration in a good way, and then you need to simply check, compare with experiments and see if this is the regime which is realized in drag reduction or maybe some other regime. So it is a hypothetical possibility, and as I will show you, it's not, it seems that at least some features which are observed in experiments are fixed by this, are fit by this assumption. So if you assume that back reaction is going to make polymer size to be inside this range, then you can use the effective equation inside this range, which is this. We neglect nonlinear elasticity, and we neglect the thermal noise, which guarantees that polymer cannot shrink indefinitely. It will make a coil with finite size. So that this is the equation on end-to-end distance of one polymer. And for many polymers, we simply turn it into the partial differential equation by changing the usual derivative with a material derivative, which you, I think, studied because it's kind of very fundamental characteristics of fluid mechanics. So polymer, of course, is transported with the flow. So in this frame, which moves with the flow, we have that. So this is by definition derivative in the frame which moves with the local flow, and it's given by this right-hand side. Who does not see this correspondence? Who sees it? Okay, I'll assume that things are good.
Correspondence with what? Sorry, I was still checking. Correspondence towards
okay.
what?
So we'll start with ordinary differential equation on end-to-end distance of one polymer. Then we introduce this, so you think of the flow as, well, let me draw this. So you think of the flow in this way, that locally there are polymers which orientations are synchronized by the gradients of the turbulent flow. Now, this orientation will slightly change as you go from one region in space to another in a smooth way. So here it will be, say, something like this, and then like this. So you have a field, okay? Now, all polymers which are in what is called physically infinitesimal volume, where physically infinitesimal volume in this context means volume where you can neglect the difference in orientations of different polymer molecules. And at the same time, this volume is, so it contains many polymer molecules. So you can think about it macroscopically. You can introduce field and you can speak of averages. And at the same time, this volume is much smaller than the macroscopic scales of variations, say integral scale, of Kolmogorov scale, all scales which you have in macroscopic description. So this is physical infinitesimal volume. Now, all polymers inside this volume, next moment of time will be, if this volume is around x, they will be at point x plus v of xt dt, at moment of time t plus dt. So all polymers inside this volume will change according to this equation. So each one of them will be evolve according to this equation. So r at t plus dt will be r at time t plus integral. Okay.
You're out of camera again. No point. You're out of camera again. Yeah.
Thank you. Okay.
Yeah,
so, all right. So the field is transported and changed according to this law, which gives us this equation of the field. Okay.
Yeah, makes sense. Yes.
All right. For whom it doesn't make sense? Is there anybody who wants to ask about it? Okay. All right. So then this is our equation on the degree of freedom of polymers. And our equation on the degree of freedom of the flow is obtained by using pi ik in this equation. So, well, it's not good to erase that, but so we have that Navier-Stokes equation becomes dTv plus v grad v equals minus grad p plus nu Laplacian v, our usual terms. And then there is a contribution from derivative of pik, which is plus d dxk and kappa ri rk. And here we have ith component of everything. And then we have this equation describing the evolution of field R. Next thing to observe is that these are, after all, simply constants. We assume that polymers are uniformly distributed in space. This is, in fact, not so obvious because you might have some effects because polymers would be not distributed homogeneously in space. However, in a steady state, due to mixing, you think that this assumption is okay. So n is a constant. And then you can introduce a field which I will designate for reasons which will become obvious with letter b, which is square root of n kappa times r. Now, the remarkable thing is that once you rescale, this equation is linear in R. So the equations will have the form which already does not know anything about the rigidity of polymer molecules or their concentration. So as long as our assumption that the scale of back reaction, which will be self-consistently determined by solution of these equations, which I write in a moment. So if all the assumptions which we made are okay, we will have that these equations hold. Here we have grad k bi bk, and here you have ith component, and dtb plus v grad b equals b grad v minus b over tau. So you see that this starts to look remarkably similar to the magneto-hydrodynamic equations for those who know them. We wrote induction equation in our lectures, which is this equation without the elasticity term. More than that, you can make the next step and show that the resemblance is even stronger because, and this is something which is not obvious at all if you think of individual polymer molecules. So this is already macroscopic property of the field. If you take divergence of equation on B, you find that divergence of B obeys simple equation, which is relaxation equation. So divergence of B is transported by the flow and decays exponentially at the rate given by 1 over tau. It means that in the steady state, divergence of B is simply 0. So after transients, there is no divergence. And this tells us that we ended up with equations which are nearly the same as magnetohydrodynamic equations. So dTV, let me write this down, plus V grad V equals minus grad B plus new Laplacian of V, and then you have B grad B. This looks, without any approximations, exactly the same as the equations on velocity field of a conducting fluid with B, which is the magnetic field. Simply the same equation. Next, B obeys the same condition of solenoidality of the magnetic field, which is again the same as in magnetohydrodynamic equations of hydrodynamics of conducting fluid. So the last equation is nearly the same as in MHD. The only difference is that instead of linear relaxation term, which we have in polymer solutions, in MHD, instead of this term, we have magnetic resistivity term, magnetic diffusivity term, which is rho Laplacian. That's the only difference. So these are macroscopic equations of dilute polymer solutions, where diluteness was used in our assumption that stress tensor is simply sum of is proportional to the number of polymer molecules. And these equations are remarkably simple. They tell us that of all degrees of freedom of polymers, the only thing which is relevant macroscopically is tau. That's it. We don't care about the concentration of polymer molecules, about the factors of rigidity which influence the constitutive relation, as it is called, between R and the polymer stress tensor. The only constant which is relevant macroscopically is this 1 over tau. And all this under the condition that when you solve these equations, so this is true if when you solve these equations, you determine some typical value of B, which is, say, RMS fluctuation. You need to check what's the typical value. Usually it's this. So then you divide it. So this is typical value of B. Then I remind to you that we defined B as square root of n kappa times R. So if you divide this B by square root of n kappa.
Come here again, please. Sorry. Come here. Yeah.
Yes, thank you. Okay. And the focus. Okay. So this is typical value of B. If you divide it by square root of n kappa, you get typical value of size of polymers, which will correspond to interacting state of elastic and inertial degrees of freedom of the fluid. And consistency of all this scheme demands that this size is between L, this is nothing but back reaction size, and larger than the coil size. Okay, so if this condition is true in the end of our calculations with this solution, and this can be in fact determined from energy consideration, you can estimate it. This is shown in papers which I sent you. So you have a consistency condition, and you have a possible interacting state of elastic and inertial degrees of freedom of dilute polymer solutions, which would hold under certain conditions, which are the existence of this range and that the result consists, is inside this range. So you have a certain self-consistent state, and then the next thing to do is to ask if it's realized in nature. So you need to see if the experiments correspond to laws which you observe by assuming these equations. And it seems that it is okay, that some of the features do work. So for instance, we see in experiments that there is some critical concentration of polymers below which there is simply no back reaction. And this we understand because it means that back reaction scale, which knows about concentration. So for small concentration, this scale would always become indefinitely large. So below certain concentration range, it will be simply larger than L. We will not be in this size. And even fully stretched polymer molecules would not be able to withstand turbulence. And that is something which what is understood. So roughly speaking, the critical concentration is determined by the condition that B square, which you determine from here, divided by n critical kappa, is larger than A. So this means that back reaction size is larger than fully stretched molecules, and even fully stretched molecules are not able to provide enough back reaction on the flow in order to change the pressure. So effectively, the number of polymers is, so we are in a situation of one polymer, so one polymer cannot change the flow, and small amount of polymers also cannot change the flow, and how small we get from here. So then you observe that in fact, the dependence, once you have back reaction, once you have the fully interacting state, the dependence on concentration of polymers seems to really be weak, or disappear completely. So this is captured by this system of equations, and it's very hard to explain these things in a different ways, because usually there would be dependence of concentration. If you have more polymers, you would think that they would react, or they would interact stronger with the turbulence. Here, it does not happen, because the more polymers you have, the only thing which it tells you is that it means that the individual polymer molecule needs to be stretched less so that it produces the same back reaction on the flow. So there is a lot of volatility here. This back reaction size can be in this range, and then any concentration which would produce size in this range would do the same thing. Then you understand also that having this range is kind of critical, because if you don't have that range, then this whole thing will become simply will not. We would need to modify it and change it and introduce dependence on concentration and so forth, and we will not have this simple system of equations. So to finish for today, we have found a simple, at least a model of interaction of elastic and inertial degrees of freedom. It is by far the simplest you can think about. So I think it's not possible to find any simpler formulation for this coupling when remaining in the realistic framework of fields and Navier-Stokes equations. So in any case, it would be good to solve it and then to try to see what is realized in experiments, what is not realized in experiments, and maybe we need to change our experiments in order to get some good properties of this system. So all these questions are research questions. They are by far not answered completely today. I'll speak of some conclusions next time. So for today, we are finishing. If you have any questions, please ask them before I end this lecture.
Hi, Itzhak.
Yes.
May I ask whether you have looked at those equations also in an energy budget style?
Yes.
Okay, and there you would see that it somehow is sometimes a dissipation and sometimes a source, essentially, or this additional interaction.
Well, this interaction takes energy from inertial degrees of freedom and pumps it inside elastic degrees of freedom.
And releases it as soon as the flow is somewhat calmed down.
As soon as the flow what?
Calms down.
Well, no, you are in a state of turbulence. It's not coming down. It's, well, I think of some, so there is some forcing here which injects turbulence. It's always...
but the area has less strain or something like that. I mean, the polymer essentially saves or stores energy.
Yes.
As a spring.
Yes.
And then releases it at some later point.
Well, there is no real, in some sense, you can think in these terms that you stretch the polymer is stretched, then it accumulates enough elastic energy, and then it starts contracting, changes the flow becomes weaker, so the polymer continues to shrink, and when it shrinks too much, its force on the flow becomes again small. The turbulent flow revives according to the laws of Newtonian turbulence. It again gets large gradients. So the polymer is stretched again. Again, it stores energy. It becomes very large. And then this process repeats. This is what I hope that...
So it kind of prevents strong dissipation events.
Yes. So effectively, this system of equations tells you that gradients of velocity field must fluctuate near the value 1 over tau. So in some sense, viscous dissipation is fixed by polymers. So if you inject more energy into the flow, it will already be dissipated by the elastic mechanisms.
Thanks.
You're welcome. Other remarks, questions? All right, so tomorrow we will have our last lecture. Please, if you can, prepare some remarks on the course, maybe some last effort to make the last lecture very useful for you. So you can send me your requests by email. Thank you.